Yes, good afternoon. This is Kelly Watt from Visual Plan. I'm going to be presenting on 3D visualization and digital twins. My background as a subject matter expert is primarily in 3D technologies. I've worked with some of the larger publicly traded manufacturers of 3D terrestrial Lidar and survey equipment. And I do sit on a number of the working groups at SIA. And I've also created the digital twin programs at Mohawk College and Georgia Tech, and sit on the advisory group for NGen manufacturing, which is a supercluster of manufacturing up in Canada. So the agenda for today is we're going to hit 4 topics. First, to start out with talking about 3D visualization in general and the difference between 3D visualization and a digital twin. We'll be looking at some lifecycle case examples of using 3D visualization. And then we'll be going into more of a technical discussion on reality capture technologies. And that will include drone-based, will include terrestrial-based, and both photogrammetry, LiDAR, and the differences between those. And we'll kind of hit a higher conversation with an ideal kind of concept of what a digital twin is and the integration of different types of data and the maturity of what digital twins are at the end of this presentation. So kind of starting off, I like this slide in terms of discussing today that we have more complex environments, more technology, and this really difficulty of managing the change, the current site information, facility operational knowledge, and the workforce turnover is really exacerbating this. And at the same time, we're expected to deal with less resources in terms of human resources. So we really need to use technology to overcome those challenges. So on a base level for site conditions, 3D visualization becomes really important to fill the gaps, to paint the picture, if you will, to understand all the details of a site. You know, we often get a heavily marked up drawing or sometimes blueprints, things that we don't inherently trust. We have a glimmer of what the site might look like. We may have some site photographs, but without having a 3D or a 3D understanding or a Google Street View for where you're going to travel, it's hard to trust that information. So as a result, there's a lot of inefficiencies where we're doing site surveys, we're doing revisits to sites, we're sharing information and knowledge through emails or conversations that are not really the true and accurate representation. And they're filtered by our own human biases and what we overlook. So when we look at what a digital twin is, it's a little different in that a digital twin is an exact visual representation of a real world entity or process, but it's also synchronized with a certain specific fidelity and frequency. What does that mean? So what I mean is that it's kept updated and current. It is something that we're going to feed historical and current information to, and we're going to use this information based on use cases to use for decision making and to have things done. Before we do the activity in person, we're going to game it out first through visual and through data. So that's a really important part, that we have historical and current information, that we're tied this process to an outcome. We're looking at use cases, and we may be involving different types of data sources. So, what a digital twin is defined today is a kind of a new trend word that's being used. But, this concept and construct of using models and information to make decisions has been around a long time. What's really new here are 2 main factors. The first is big data and the availability of big data through AI and sensors, and to be able to manage that data, crunch that data, and to analyze. And the second is reality capture technologies, and the fact that we have very efficient ways to capture accurate, high fidelity information and to bring that into platforms we can share and collaborate from. So that's what we're going to talk a little bit about today. So where do we see value with visualization? And I could say that we're going to see this from a life cycles perspective. And from a digital twin perspective, a digital twin is life cycle. It is the construct in the design of how we're going to build something, but it's also even just as important or more important, how do we operate and maintain that asset or that facility or whatever that might be. From a security perspective, this could be a little bit more of a subset of looking at our cameras, our design, our implementation, and how in a real-time space, how do we operate these with the business functions and the processes and the workflows? So, what do we get from benefits? Removing the site visits and reducing data silos are critical, that we have current and accurate information, and that information is collected over time so that we're updating that information and it's always current. That we have clear communication through visuals. This is really a fundamental aspect of how we communicate as creatures. When we see things and we walk through a space and we share an understanding of a photograph or 3D space, we can define and classify what we see and we digest that information completely. And we have a common understanding. Red is red and green is green, and a square is a square and a circle is a circle. But we've seen that we didn't have to describe it. When we have to describe it and use language, and we have different definitions for language, that's where miscommunication happens. That's where some of the breakdown happens. So to be able to visually game out best outcomes on a common understanding of visualization, we can have a lot of efficiencies and reduce the mistakes that happen commonly from misinformation, miscommunication, or more importantly, from not having adequate information and speculating under things that we don't actually know, and guessing. Now, from the operate and maintain stage, it's really about building in the processes to work with visualization, to understand a process. And it's really about, managing knowledge from a visual perspective. Walking in a room, instead of looking at a tabular report, looking from page 1 to page 50 of an operator manual, is to be able to look up and touch an object and then see all the history and the information behind that object. So that's really the truly amazing thing about 3D, is the way we can organize the world by how we see the world, as opposed to the construct of reports and tabs and spreadsheets. So let's talk a little bit about modeling, 3D modeling in general, and how modeling has advanced design and an operational organization's understanding of how we keep our operations going. So one of the first applications for 3D models came from the construct of the Concorde, when wooden models were used to replicate the building process. And having that physical model, that digital twin in that sense, at that time, it wasn't digital, it was physical, was so instrumental in the aerospace industry. There were so many findings of efficiency that was a game changer, and that set the industry standard moving forward, that they were going to use physical models. Now that moved into complex plants and printing off plastic models and being able to have exact replicas, physical 3D replicas that we could see and understand, and the relationship between those aspects of that model would really help us understand how to build it properly. And you would even see these in the real estate world. When I was younger, we had, models that we would, laboriously put together and glue together to actually have a replica so we could understand it before we build it. And then we had the advent of 3D models from a CAD perspective, and moving from a 2D diagram to start to have elevations, and looking at egress and how clashes come into play. That really accelerated the world of effective design and effective construction. The 3D modeling environment helped to foster the robotics and automation world, because we needed to simulate, we needed to understand space, we needed all of that information to create the repeatability and simulate processes with robotics. And within the last 10, 15 years, the rapid available technology in the reality capture space, from drone technology to Lidar and photogrammetry, has really advanced how we collect the physical environment in an accurate way, moving beyond a 2D photograph into 3D reality capture, so that information can be used in many different ways, in the design, in the construction phases and monitoring, or in the operate and maintain space. And one of those kind of offsets is in 3D printing, or looking at taking parts of the manufacturing process and being able to construct a model or a part from reality capture. That's really quite fascinating of how that industry has really evolved. And then taking this 3D information and be able to consume it in different ways, like in augmented reality, VR, mixed reality, and XR. So, reality capture has been the driver of the 3D visualization and 3D modeling, and it's made the process much more simple and accessible, less costly as well, and allow us to get more current information more frequently. And really, this is the birthplace of the digital twin, looking from the design and build, but also in the operate and maintain space. So taking just a quick look at these types of wearable headsets and what they are, we have virtual reality, mixed reality, augmented reality, and extended reality. So the primary differences in these different types of technologies, they all wear a headset, but virtual reality is a completely immersive digital experience, and it's not really safe to be headset on, blind, walking through a space. So typically, these are controlled environments. Oculus Rift is an example of a VR headset, and this is traditionally used in design concepts and also used in training. Now, mixed reality will mix the physical objects, and we can interact with these digital objects. But we can also do this in a space where we can have some visibilities, more situational awareness. HoloLens is a good example of this. And mixed reality will blend the physical and digital worlds to produce new environments. And we can coexist between the real environment and the virtual environment, the space. Now, augmented reality and headsets like the RealWear, we're seeing just a digital uniocular lens, which the operator from Shell has, and they can reference almost like an iPad up close and communicate with someone remote on anything from CAD drawings to BIM to process to video to workflows, and also have a headset to communicate. So that remote communication with visualization and augmenting that process, but allows us to be hands-free working in a real environment is really, really part of what that really means. And then the extended reality is combining all of the real and virtual environments using human-machine interactions to generate different scenarios. So there's a mixture of those things. So I think it's important to kind of understand and delineate the differences between these technologies and the use case or business case that come from them. And understand these aren't going to solve all the world problems, but based on use case, they can be tremendously valuable, especially when we're looking at environments where there could be an element of danger, risk, or there's repeatability from a training and knowledge management perspective. So let's talk a little bit about visualization and this idea concept of 360 imagery and how this is really changing the indoor documentation space because of the rapid nature of using 360 video, even on a hard hat like that or on a robot, and to be able to walk through and to process 3D data from a camera that costs $300–400 is really quite tremendous. And some of the platforms that are available today, either you can do it yourself or you can use service providers to create 3D data very cost effectively. So a couple examples, use cases that we've been involved in with consultants in the SIA community, or SIA community rather. We have a hospital design that was done by Butchco ESI. The project was 1 million square foot. 3 days of data capture were used on the project to collect the physical environment from which we needed to audit the existing hardware locations, and then use that information to construct a new design concept, but also to communicate that information back and forth between all of the stakeholders. And that really is where a key benefit of visualization is as a communication tool. So what we found on this 700 camera design upgrade project, multi-building medical campus during COVID, dealing with HIPAA compliance, all these challenges, what we were able to do is the entire project was designed with only one site visit. And I think that's really, truly impressive in that we can replace the back and forth, the visual confirmation of information from a site visit, the disruption that we have from having to have stakeholders come out and either gather information for you or escort you through a building, and to be able to save on that time, the schedule, or the rework that happens as a result of having inaccurate information and making poor decisions is really tremendous. So it also helps us with the approvals. It also helps us with just the confidence level owners, operators have with the design process and being engaged in the design from the beginning. Another example we did with a federal building using a very low level 3D model, just really constructing that from the ground up using the CAD drawings, and to be able to place the exact make model of the cameras and the license plate readers, and other sensors to be able to visually display both in the 3D, but also with the context of the current environment using the 360 imagery. So in this way, we can walk around and truly understand, everything from where the sensor or IoT device is going to be installed to the cabling, conduit, power source, and the physical environment that may prevent or make it difficult for us to execute on the design intent. So there's a lot we can get from a 3D model like this, or a building information model or design, and it can show us kind of how we plan to execute a design project. What it doesn't show us always is all of the intricacies that we see from the current environment, the current existing characteristics, egress, shadow, materials, flow of people, all of these types of things, usually require some type of site visit to record that information, photographs, video, etc. So being able to consume this data side by side like this can be extremely valuable. Another use case example with a sensor, which was a radio frequency sensor company that needs to design a layout of hundreds of sensors in the building for presence detection and occupancy management, and also vital monitoring, is to be able to understand, well, where to place these, where to place the PoE or the gateways, because it's radio frequency. How does environment, what are the aspects that are going to make this design fail or make it successful? When we look at the 2D diagram, it's limiting. It's very simple for us to block dots on a diagram, say, well, this is where we're going to place them. It's quite another thing when an integrator goes to the site and needs to install these things. You can see all of the holes in the roof or missing tiles, or where I was hunting to find the PoEs and the gateways because I didn't know where they were. And that took a lot of time and effort to do so, when we could physically record the locations of these through imagery and have that tagged and the asset, make, model, and serial number. Now I can always go back and find that precisely in the future, especially if I have some type of notifications telling me there's an issue. 3D visualization is also extremely helpful with wayfinding, especially in complex environments, manufacturing, oil and gas, power utilities, and to be able to concisely consume how we do a route, where we go, how we do it safely, to find specific and small things that may be very difficult to find. Drone inspections in confined spaces are also coming more and more common, where we can place a device in harm's way or somewhere where we can't get a human and be able to record things like we've never been able to record those in the past. And sometimes that's a video that we're creating. Sometimes that's a 3D point cloud, as we're seeing here, and be able to document things, to look at welds and rust and crack and corrosion and things of that nature in a way that we never thought was possible. So, using reality capture technologies to leverage not having to place a human in this space, to not have to put eyes on something, where we can place, instead of eyes, place a camera, place Lidar, is really quite fascinating. So when we talk about constructing, both the current conditions, which we'll see in the point cloud here in these images, and the design concept, which you'll see in the colorized objects that we're going to install, working in a digital twin or in a design platform, we can go through the motions to simulate a process. And that can include involving, scissor lifts and people and flow, to game out, and this is a key thing, is to game out the best outcomes, so that when we execute safely, we execute without mistakes. And there are many considerations that are already identified, issues that we identified and remedied before we get to site. Something as simple as a boiler not fitting through the door and getting into a space or up a stairwell can cause massive problems, which is a simple problem to game out before we start. So simulating unexpected outcomes can be a big game changer using 3D visualization. So another case example for simulation with 5G coverage in the US using an NVIDIA platform, really we saw some tremendous benefits. So 5G networks, 15 million microcell and towers to be deployed globally. That's a big problem, and there's a lot of environmental challenges. So Ericsson is currently building out city-scale digital twin cities to help them plan and optimize the 5G microcell and tower placements. Imagine placing towers in inefficient places where we're not going to get optimal results. So, again, be able to do these processes digitally through visualization, whether it be through simulated data and scenarios, whether it be visual scenarios, and looking at it can have tremendous outcomes. A couple more examples from power utilities, where we're using drones instead of climbers, using drones instead of helicopters to more efficiently document various physical hardware and assets for issues. In this case, we're using even thermal imagery to detect heat and anomalies. This can be something that we are also augmenting with artificial intelligence to go through hundreds, thousands of photographs to look for and to detect, based on object recognition, what these defects look like, and to help draw attention where issues are that need to be found. And then looking at different levels of zoom cameras from drones that we can get very close to assets and even read text on a wind turbine like this, or to understand types of cabling going in a satellite tower without having to physically be there, using a high resolution output. These are being commodified workflows today. So let's talk a little deeper on what are the available reality capture technologies in the space. How do they operate? What is the best tool for the job? Because we want to be as efficient as possible for what technology we're using. So terrestrial LiDAR is commonly a technology we use for modeling, the technology we're used for monitoring and high precision documentation, millimeter accuracy. So typically the instruments are a little more expensive based on the sensor you're acquiring. You'll get a better quality of result, but usually using a tripod, usually needing to have that to scale, introducing targets. So there's a process here. It sometimes is a time-consuming process. It's an expensive process from a hardware perspective and also from expertise. And there's a lot of station moves. You have to move this because it's line of sight. So from a high fidelity perspective, from an accuracy monitoring perspective, this is the right tool. But understanding what your needs are is really going to dictate what technology you want to deploy. Another rapidly growing technology, SLAM, which is simultaneous location and mapping, applies LiDAR with various other sensors for us to be able to move while we're collecting the data. So these are mobile LiDAR units that are using various sensors, RTK, using IMUs, which we'll discuss in a moment, to be able to locate the position of these point clouds and scans. Accuracy is less, noise level, meaning the artifacts or the relative defects that we'll see in the laser scan are higher, but from a practical perspective of being able to capture it quickly and large scale, it's a tremendous opportunity. And we're placing these on drones, we're walking around with these, and even your iPhone itself has a mixture of photogrammetry and LiDAR directly on your new iPhone. So you can capture small spaces, objects with your iPhone and create point clouds to 3D model from, or just to use for visualization and measurement. Really, truly tremendous. I come from this space, and really even seeing the last 5 years, the rapid adoption and creation of new LiDAR-based technologies is really, really fascinating. So other types of things that we can think about are aerial photogrammetry. So different cameras that we're placing on remote sensing devices like drones to be able to capture large scale information, and then to take that information, mesh it, model it, create 3D information or 2D topo mosaics, or even other types of data sources can be really valuable. As we spoke about already with zoom cameras for visual inspections, mounting high resolution cameras onto drones allow us to get very good detail on difficult to reach assets, and also looking at, sorry, my slides keep pushing ahead, other types of multispectral, whether it be thermal or infrared, to even multispectral, where we're going to be able to do things like moisture, crop health, weeds, insects, do some modeling and prediction from this, looking at methane, and all of those aspects help us to look at large scale data in a much more efficient way, and to be able to make actionable decisions with real information, with more than data, with visual carbon copy, if you will, or current conditions of what we're capturing. So what are the critical components for mobile? There's two things that we should know about, and the quality of and the setup here, the complexity can be a part of the deliverable is working with a GNSS and an IMU. So the global navigation satellite system or a base station that's communicating to a satellite on the position as we change and document is going to be critical for drone mapping, for SLAM sometimes. And the quality of that is going to dictate the actual measurability that we get, the quality of the data. Likewise, the inertial measurement unit, the IMU, will be able to give us physical sensing of where we are in space. And some of these sensors are, $80,000, $90,000 are used to project rockets into space, but the IMU is a critical component. So again, the more complexity we add, the more we may need a service provider. We might need to lean on technology to be able to solve these problems. So common things with LiDAR and photogrammetry are line of sight. So whether you have a drone that's over a canopy of trees and can't see below, or a terrestrial scanner on the ground, we need to reposition the line of sight so we capture the data we look at. Registration. As we're capturing data, whether it be a single laser scan or photographs, we have to way to combine these different data, individual data sets or individual coordinate systems into one laser scan point cloud or one deliverable. So there are different ways to do that. There's software to help. There's artificial intelligence to help. There are also the process of having physical targets, or to actually have a total station that measure out actual specific targets, or to use like an RTK network, real-time kinetic, to tie into an existing GPS system and to add controls. So the idea is, what level of accuracy do you need for your project will dictate on the types of sensors we use, whether we use LiDAR or photogrammetry, and really what does that look like? Because it can be a major cost difference based on the level of accuracy and what we're going to use the data for. So some examples of targets: checkerboards, spheres, other types of markers can be used. You may see these on scenes. What they're used is give a specific coordinate point that we can tie some information visually to other visual information. And from a photogrammetry perspective, we're going to rely heavily too on the overlap, the pixel match. And when we look at certain environments that are very feature rich, it makes it quite easy for us to merge these data sets and to find commonality, to piece them together like a puzzle. But when there's very little physical attributes in these spaces, like a white hallway like this, it makes it much more difficult. So that changes the workflow. We may need to do a different type of capture. We may need to do more pictures, or we may need to address environmental challenges with different workflows. So something to definitely consider. So we talked about a lot of different data sets, and what are we going to do with this data? We have visual data, we have analytics, we have telemetry, we have different types of video streams from cameras and access control. So what do we do with the data? And the idea of this kind of construct of a digital twin, and it doesn't have to be citywide. It can be application specific. It can be small in the outcomes that we're looking from, but it's the ability to integrate, to converge this information into an interface that we can read and understand and share and update and make decisions from. Most importantly, to make decisions from. And that might involve a simulation aspect. It may involve running through specific workflows to get to certain outcomes. So in the NVIDIA world, and we all kind of know NVIDIA as a graphic card creator, they really actually are one of the foundations of AI. They have a 5-stack AI stack that's feeding a lot of video analytics and a lot of different technology today. So in their definition, it is not only that we have a visual replica of a physical reality, but also this rich interface of the information that is associated with it. So, how do we synchronize this information? How do we make it interoperable? How do we bake in AI? How do we bake in workflows? And it can be anything from a maintenance workflow to something that's on a simulation scale. So what we're going to show here is what NVIDIA in the next slide is doing with autonomous vehicles. But from a factory or a facility perspective, what these data feeds or these data threads, what do they mean? What are they? Anything from workforce management systems, CMMS systems, integrity management systems, from doing inspection work and routine maintenance? What are the documentation aspects that we need of assets, components, systems, and buildings, right? And then what layers of analytics or fault detection and diagnosis, what types of automated controls, what does that look like from an AI and machine learning perspective? And then into the SCADA and the telemetry of smart buildings. And that is definitely including security technologies, IoT devices, et cetera, and looking at the trending historical data from the analytics perspective. How do we optimize? How do we identify issues? How do we resolve issues? You know, this is what we're talking about, constructing that in a 3D world so we can look at it, access it, and use that information more intelligently. So let's look at a kind of real-to-life NVIDIA OMNIVORE example using synthetic data to generate different scenarios that we get from autonomous vehicles driving in a real-time environment. So as you can see, this is pixel accurate. We're looking at the colorization to understand depth. We're understanding objects and their physical space, understanding speeds. All of these are data threads that are feeding into this environment that we're simulating and trying to teach or learn how to do things safely, or to teach them how to do a certain process. So kind of in that final kind of example, I wanted to tie together what a digital twin could be. And 3D visualization can be as simple as taking a virtual tour of a space and adding that into your design process, right up to an operational simulation, AI-driven, real-to-life environment where we're using this data to solve many different problems. So from that perspective, there's a maturity and there's an understanding that we don't have to be the NVIDIA OMNIVERSE on our first step. A lot of this starts with gathering the data threads. And the data threads can include reality capture, starting with 360 imagery or Lidar, creating proper updated designs and 3D models, and start to look at the picture to the diagram. And then start to look at that information. Well, what information can we feed into that? Project schedules, other types of simulation information. It could be other data feeds. And how does that data feed match with the actual physical context? How does that help us to solve problems? So we get into this static, feeding that information manually, to feeding it automatically, to bidirectionally feeding and pulling data between the 3D world and the data threads that we're feeding into it, to potentially an autonomous world where the digital twin is reacting and controlling and changing based on the feeding information in and out. So again, most of us are really at this level here. This level is into the advanced manufacturing, some oil and gas spaces, but kind of understanding how to talk about this and what the phases are, I think is important for us as we start to try to have a common language on what is this idea of 3D visualization and reality capture and modeling, and what is this concept of a digital twin. And a digital twin is really unique. It's unique to the use case that you use it for. It can be as simple as monitoring a SCADA system, a pump or security system, right up to a full-blown operation of an autonomous car or a building and looking at all the aspects in that building. So if you have questions on digital twins, on 3D visualization and reality capture, that is what we do. We work in the space, we provide services, speaking and training, and we really want to foster awareness, and we want to share ideas and to help the community think in 3D. And that's it.